Uh, okay, welcome to this class. I think I want to make it full screen. Yeah. So, in this week, we'll be discussing about polymer melts and, in the same context, about glassy polymers. What are polymer melts? I shall just explain in the next slide. But while talking about polymer melts and glassy polymers and what its phase diagram is, we shall also have to talk about a bit about scattering, and then from scattering there will be a module on statistical physics and microscopic structural quantities which we actually measure in scattering physics, and those are also the things that we calculate, and that is going to help us understand the physics of glassy polymers and polymer melts and so on and so forth. So that's a separate addendum, a separate set of lecture. Scattering is included in polymer melts, but some of the statistical physics will be explained in a separate lecture, and we will also at the end come to the idea of correlation hole in polymer melts. Okay. So this is what we'll be discussing. We'll start with polymer melts, go a bit into scattering phenomena, and thereby describe some of the statistical quantities. Using that, there will be a separate module on microscopic structural quantities and glassy phenomena, because only knowing that you shall be able to understand the physics of polymer melts, and at the end come to the idea of correlation hole in a greater detail using all that has been built up. So what is the basic message that you must take about a polymer melt? What is a polymer melt? Polymer melt is essentially the way you can visualize it. Suppose that you have a plastic mug in the kitchen or in the bathroom. That's a solid, that's in a glassy phase, and once you heat it, right, you take that mug and heat it, it will melt to form a liquidy polymer substance which can flow. So that's a polymer melt. It is different from a polymer solution in that in a solution you have a huge amount of solvent in which polymer molecules are floating around. They might interact, not interact, or in a semi-dilute solution also. And there might be polymers touching each other, but in between the polymer chains, there is a lot of solution. In polymer melt, you have no background solution. All that you have is polymer chains touching each other. Okay, in that sense they are really a material. I mean, all the atoms of which all the atoms which belong to the monomers of the polymer, they are touching each other, and between them there's nothing but space in between, a bit like what you would see in a crystal, except that in a polymer melt, the polymer chains can move past each other, they can flow unless they are cross-linked, but that's a different topic. We'll come into it detail. So polymer melt is a material full of flowing liquidy polymer chains which can pass uh, by each other if they are not cross-linked, and even if they are, they can flow to some degree, and the viscosity is very high, especially if they are entangled, especially if they are long chains. But that's liquidy polymer is what is polymer melt, and when you go take them into uh, low temperatures, you essentially obtain glassy polymers as different from crystals. So for normal, I mean, the condensed matter stuff that you read there, if you cool down materials like sodium chloride or various metallic ions, you get into a crystalline phase. But for a polymer, you don't get into a crystalline phase, you get into a glassy polymer phase. But what is glassy polymers? We'll come to it later. Now, in the liquid phase, the most important and the most surprising aspect which you could register. So in a polymer melt, you have large number of polymer chains interacting with each other, but the conformation of each of the ideal chains is that of sorry, each of the conformation of these polymer chains is that of an ideal chain. It is a Gaussian statistics. This is a Gaussian spread. Now that you should find very surprising, because you essentially have a large number of chains interacting with each other, densely packed with each other in a polymer melt, and you get ideal chain statistics in terms of conformation. It does not mean that the polymer chain is ideal, in that the monomers are not seeing each other. They are not ideal. Polymer chains cannot pass through each other. Excluded volume interactions are felt, but the conformation is that of an ideal chain. So what is the picture that you should have of a polymer melt? It's something like this. Each polymer chain is represented by different colors. They are touching each other, and sometimes there's space in between. It's, as I said before, melt a plastic material, you will get liquid viscous stuff, and most important, no solvent in space between monomers. So that's what a polymer melt is. And they can flow even if entangled or unentangled. If it's entangled, its viscosity will be very high. But if it's unentangled, relatively low, and it's cross-linked, then it can flow to some extent, but it will have some solid-like characteristics. So this is dense polymer melt, where large number of polymer chains are interacting with each other. So what are the kind of questions that you can ask? So some of the questions that you can ask is basically that so are the polymer chains, they are of course densely interacting and touching each other, but are they in this form when where they are entangled, and each chain, the space of each chain is occupied by monomers of other chains as well? Or is it like this, where you see, yeah, there are polymer chains which are touching, so this polymer chain is might be touching the monomers of this chain, this chain, this chain, this chain, this chain, and so on and so forth. But you see that in the region of one polymer chain, self-avoiding polymer chain, in this region you don't see too much, except at the peripheries, the monomers of other polymer chains getting inside the space of this. So which picture is the appropriate one? So this picture has been taken from Scaling Concepts of Polymer Physics, a book by Digens. And what happens is that this is the right picture that you should form in a 3D polymer melt. But in a 2D polymer melt, or a polymer melt which is confined strongly between two parallel plates, then because of self-avoiding interaction, this seems to be the more appropriate picture in 2D, in high confinement. Or if it's a truly 2D, then basically you have polymer chains interacting with its neighbors, but they don't invade the space of a central polymer chain. Each has their own space. Right. Now, what I should also introduce is the idea of a correlation hole, and also give you some idea about why a polymer chain in a melt behaves, its conformation is that of an ideal chain. And the basic idea can be thought of like this. So suppose this is one particular polymer chain just colored in white so that you can identify it, surrounded by other chains which are marked black. They are not any different. The reason this has been marked white is only for your visual help, right? So then what you see, so what has been plotted in the plot below is basically the density of monomers as you as you go across this region. And then what you're going to see is that the density of the white monomers gradually increases in as you approach the center of mass of this white polymer chain, and correspondingly there are fewer number of black monomers in this. Yes, in 3D they are overlapping, they are intersecting in the space, but the density of monomers relatively is less here. But there are but there are no more black chains, relatively speaking, as you go away from the center of the polymer chain. Now, this figure is also taken from the scaling concepts in polymer physics by Pierre Redigens, and so this is what I have written down here essentially. And to understand why you get ideal chain characteristics, you should think why you get, so in a self-avoiding polymer chain, you get swelling. Why do you get swelling? You get swelling because the monomers of the same chain want to avoid each other. There's some excluded volume interaction, and as a consequence, they want to spread out, right? They want to spread out, and the extent of the polymer chain as measured by radius of gyration goes as n to the power 3 by 5, and being the number of monomers in the chain. Now, for this chain, as this the monomers of the white chain want to swell out, what do they see? They see the monomers of the black chain, or the black chains, right? So here near the center of mass, the number of monomers of the white chain was the maximum, but a polymer chain wants to swell out to avoid monomers of the same chain, and that's why it can swell as it goes towards the periphery. But as it goes towards the periphery, it sees monomers from the other chains, which push it back. A consequence of this is basically, uh, though monomers feel excluded volume interactions and self-avoidance, they are compressed back to form an ideal chain conformation. So this is the basic physics. Now, to show it analytically, one has to use self-consistent mean field theories, which are rather advanced theories, and even them they have then even if you write down the equations for the densities of suppose the white chain, and how that is coupled to the density of the neighboring chains, and solve it self-consistently, it has to be solved numerically. So we are not going to the advanced theories. That the ideal polymer chain, sorry, that the polymer chain in a melt behaves like, in the sense of conformation, like an ideal Gaussian polymer chain, can also be uh, established experimentally. After all, have, being able to establish it experimentally is finally the proof of the pudding. It has also been verified computationally by large scale computer simulations, where you make a polymer chain in a melt of other polymer chains, and again you see Gaussian statistics, conformation statistics for a polymer chain. So as of now, as of 2020 and 2021, this is well established, whether theoretically, experimentally, or computationally. Okay, to talk about computationally and talk in more detail, we have to introduce the idea of a correlation hole, a region, uh, a dip in the scattering intensity. But for that, uh, and how to figure out how does one find out the conformations of a polymer chain in a semi-dilute solution or in a melt, and so on and so forth, I shall introduce the rudimentary ideas of the scattering theory. Okay, we can't, of course, go in great detail, but just an idea before we come back towards the end and introduce the idea of the correlation hole, to establish how we get that polymer chains in a melt are ideal. So this is the essential basic physics. Okay, this is the basic message. Okay, so talking about scattering, scattering has been described in Rubinstein in multiple sections, actually, in the first chapter, in the second chapter, in the third chapter, and also when you're talking about dynamics, it's in the chapter 8.9. Uh, so using scattering, we can figure out a lot of things. We can figure out interpolymer chain interactions, the conformation of a single polymer chain, okay, in the dilute regime, in the dense regime. But let's start with the dilute regime because it's simpler. And we can also figure out yeah, so molecular weight, interchain interaction, interchain intra-chain conformation, and so on so forth. Okay, so we shall be discussing about light scattering, and we shall start with the dilute polymer chain, where you have a solvent and the monomers or the monomers of the polymers are dispersed in the solvent. And the key idea that shall be used to understand scattering or to measure the properties of the polymer is that the solvent, background solvent, and the monomer or the polymers have different refractive index in the different regions from where light is scattered. The monomers have a different refractive index, right? Now, though I'll be talking about light scattering as you go to smaller and smaller length scales. So, as you know, light has wavelengths of 400 to 600 nanometers, 4,000 to 6,000 angstroms, which is big in terms of the sizes of molecules. But if you go to smaller length scales like nanometers or smaller, one typically uses X-ray scattering as different from visible light scattering or neutron scattering. In each of these cases, basically the solvent and the monomer of the polymer have different electron density differences, uh, due to which you get X-ray scattering. Scattering is different from the solvent regions and the monomer regions. And in the neutron scattering, there are differences in the atomic nuclei for the solvent region and the monomeric region. So depending upon whether you're using visible light or X-ray or neutron scattering, the scattering contrast, okay, the difference of scattering might come from different physics, as in electron density difference within an atom, or the difference in the atomic nuclear case, or for visible light refractive index. But that is going to be, the scattering contrast factor is going to be a prefactor in the intensity of the scattered light, as normalized by the intensity of light which is incident, right? So it is going to be a constant prefactor. So we are not going to discuss that. We are more interested in how the different conformations or the interpolymer scattering from polymers separated by a distance r, that affects the scattering intensity. Okay, so we shall pretend that we are talking about light scattering only, but actually, as you look at different length scales, you will have to use this or this, but that will be basically in the prefactor of the physics. There is a corresponding physics to that scattering phenomena, which we are not going to go into in greater detail. Okay, so we begin by Rayleigh scattering. So what is Rayleigh scattering? Rayleigh scattering is typically discussed in the context of scattering from gases or liquids. And suppose you take polarized light, so that light is incident in this direction, the Z direction, say, on some solvent or molecules, which is in a scattering volume V, and the electric field is suppose oscillating. Electric field of light is oscillating in the x direction, and the magnetic field By is oscillating in suppose the y direction, and the plane wave can be written as B0 cos 2 pi nu t, nu being the frequency, minus z by lambda, right? And this light, and similarly there will be an expression for the electric field, and suppose that this light is incident on a on a system, on a scattering volume containing scatterers, right? And if you have visible light, what happens is when light is incident, these electric fields and B fields are incident. Electric field is much stronger than the B field. Then the molecular electron cloud experiences an electric field due to which it starts to oscillate. The electron cloud starts to oscillate, which results in a time dependent dipole. So a time dependent dipole is induced. So you have basically separation between the positive and the negative charges, and you have a time dependent uh, dipole which oscillates. And if you have a dipole which oscillates, right, then the dipole moment which is induced can be written as P into alpha polarizability into the incident electric field. And if there's a oscillating dipole, it will emit radiation in all directions, which in turn is the scattering electric field, which will be proportional to 1 by c square, c being the speed of light, 1 by r, as electric field basically goes out, there's a decay of 1 by r, and it depends upon d2p dt2, right? The double derivative of how fast the dipole is changing. This is the dipole moment. The dipole moment in turn depends upon alpha into the incident electric field, the strength of the electric field, and so on and so forth, right? And the electric field at a distance uh, r will depend uh, on the dipole oscillation at time t dash, which is the current time minus r. R is the distance from is the distance r from where you are measuring, from the where the dipole oscillation was taking place at time t dash. So this distance r by c is the time evolved, is the time it takes for a oscillation scattered radiation to reach point r, suppose, which is here, right? So that's how the electric field will be formed, right? So the electric field scattered when you take the double derivative with respect to time, right? So you had this was the electric field, and now you have taken the double derivative with respect to time multiplied by alpha and so on and so forth, which give the polarizability. So then the scattered one, and when you take the suitable derivatives with respect to time, and the nu comes out, and nu you're replaced by c by lambda, and so on and so forth. So then the scattered intensity you get as the electric field, sorry, not the intensity, electric field, you get as 4 pi square by lambda square. Uh, right, this 4 pi square also you get on taking the derivative, 1 by r polarizability ei, and this was the equation, and you have written as c by lambda to get this, right? And then the intensity depends upon electric field square expectation value, and that in turn becomes 6 pi to the power 4 lambda to the power 4 r square polarizability square incident intensity. And here you see the famous 1 by lambda to the power 4 of Rayleigh scattering, which happens due to dipole oscillations. This is what would happen if it happened from one molecule. Now, if it happened from n molecules, then this intensity will be proportional to the number density of these molecules into E square T, same as this. So what is Cn? The number density. So number density is not a quantity you directly measure. Instead, you typically have access to the density of the polymer, and you have also access to the molar mass of the polymer, which you already know, which you have added. And then you can calculate the number density from C by molar mass by Na, which basically M by Na, if you put Na here, M by Na is basically the molecular weight of a single polymer chain. Okay, Now it can be shown with optics. Here we are just using the results that the change refractive index n square is proportional changed due to the addition of polymer to the solvent. So the change refractive index n square is proportional to the refractive index of the solvent square plus 4 pi alpha polarizability into the number density of the polymer chains. And from here, if you can if you can directly measure the change of refractive index with the concentration with the density, then you can measure the polarizability as n by 2 pi dn dc. How does refractive index change with concentration m by na, which you plug it in here because you didn't know what was the value of polarizability. You have to do a different experiment to do figure out dn dc, from where you get polarizability, and then you plug it in this equation, right? And if you do that, you get the scattered intensity from n scatterers to be 4 pi n being refractive index square lambda to the power 4 r square dn dc, which you measured in a different experiment to figure out polarizability, into number density of polymers into the incident intensity. Now, if you write the scattered intensity, normalize it by the incident intensity and multiply it by r square, because this quantity is going to decay as you go farther away from the scatterer as r squared. Now, if you write it like this, you call it the Rayleigh ratio and represent it by r theta, which in turn depends upon some constant kappa, which is like 4 pi n square lambda to the power 4 dn dc into Cn. Now, if you measure this, and that's what you measure in a scattering experiment, then r theta is this constant into C m by Na. Now, if you know the density, if you measure this, which you have to measure, then you get the molecular mass of the uh, of your polymer. Note that you are using time averaged intensity, right? So this is how you get it, right? So you get dmdc from some other experiment, measure this quantity, scattered intensity, normalize it, measure this is proportional to some constant into Cn, which you can write down in terms of the molar mass. Now, now, now going further ahead, now consider one polymer chain. So this is from section 2.8 of Rubinstein, and consider one polymer chain in the solution. Okay, you have incident light with the direction of ui, and this red thing is a polymer chain. Okay, the non-overlapping dilute polymer chain, that's what you are considering. You have a dilute polymer. So this light comes here, gets scattered from this monomer and moves towards, suppose, this direction uj. Okay, and this polymer, this light basically gets scattered from some other monomer here, and again it bends angle theta, and it moves towards this direction, in the direction of uj, and we can get these two lights to interfere. The angle of bend is angle theta, and the distance from one monomer to the other, both of which due to scattering has bent angle theta, and whom we get to interfere, uh, this this distance, this vector between these two monomers is represented by rj, right? And we can calculate the path difference, which is the distance ac, which this light has traveled extra, and OB, and the distance between these two distances gives the phase difference between this and this. right? And the phase difference can be written down with a little bit of algebra as 2 pi n being the refractive index by lambda ui minus uj, these two unit vectors ui and uj, into rj. So basically what you have to express this distance in terms of rj and this distance in terms of rj and theta. This is what you will get. And uh, basically then this phase difference from due to scattering from these 2 points can be written as phi j. If this is the center, if this you consider this to be the origin and this to be j, this can be written as q vector dot rj, rj being this vector, and q vector is 2 pi n by lambda ui minus uj. So if you change q, you are essentially changing uj, because if you are taking a monochromatic light, lambda is the same. You change uj, different angles of scattering, you are changing q. So from the same point you can have different. So if you change the where you are collecting the light for interference, if you change theta, you will get different values of q vector, and the magnitude q can be written as, after doing some algebra, 4 pi n by lambda sine theta by 2. You will look up the books if you want to get the derivation. Message: you change q by changing the detector angle theta by 2, and that leads, and as a consequence, in this direction, the electric field that you get is incident light. A depends upon basically the scattering, contrast, and other factors. Cos, so this is the incident electric, and this is depending upon other factors, right? But in terms of phase difference, you get uh, due to j, scattering due to j, where this point is taken to be the origin, to be cos 2 pi nu t minus phi j. So this is the phase difference of this from this. This has been taken to the origin. And if you want to look at the scattering from all different points measured at angle, particular angle theta, which decides a particular value of q, then the total electric field will be sum over all j, all other monomers, sum over all j, and cos 2 pi nu t minus phi j, different phase differences from different monomers, right? Intensity, the scattered intensity will be es whole square, and time averaged over the time cycle, right? And so basically you take enough averaging uh, over a time cycle, and more actually over different conformations, but we'll come to it. And this leads to 2ia square. Okay. uh, okay, so if you time average or time cycle only, uh, so some of the terms remain, the cross terms remain actually, the whole square terms actually get averaged out when you average over a time cycle. And so what remains is basically uh, this sum whole square, okay, into dt, okay. And then I think this factor of 2 shouldn't be here. I'm not sure. But you're basically taking each of those terms and doing a whole square. And on taking an average, what survives is basically only the cross terms survive. And what you get is the scattered intensity is proportional to the incident intensity a square, whatever the factor scattering contrast, sum over k equal to 1 to n, j equal to 1 to n, phi k minus, this should be j, not phi I, but j. So basically, take any two scattering centers, take all pairs of them, all possible pairs of them, and the path difference. So the scattering intensity at a particular value of q depends upon the path difference, phi k minus phi I, the difference in phase, which in turn depends upon the path. Now, the form factor PQ is defined as IS by IS0, where there is no scattering if the light passes straight. So this is Q, which has formed an angle, and this is Q equal to 0, which means it has passed straight, light which has passed straight without a scatter, and that's what is basically the form factor. Now, I scattering 0, it in itself is dependent upon I, the incident intensity, into a square and number of scatter square, right? Because but so is this, right? That this is also dependent upon number of scatterers, but that will come in later, right? So PQ is EI into a square, double sum this, all possible scatterers, and the one which has gone straight is dependent upon the number of scatterers. So basically a square cancels this a cancels, ei and ei incident light cancels, and what remains is that the form factor is essentially dependent upon 1 by n square summation k equal to 1 to n, j equal to 1 to n cos phi k minus phi j. And this in turn, phi k and phi j can be written as q dot ri, and phi j can be written as q dot rj summation as usual, which is of course equal to 1 by n square. So this is cos. It can also be written as real part of e to the power I q dot ri minus rj, which is the relative position between two monomers, right? So this is the form of PQ. Now for very small q, okay, small q, small scattering angles, and take if you average over all conformations, so basically you have this, right? Now suppose ri rj can change and you do an ensemble average of all conformations in an ideal, assuming the ideal chain, if you take all possible conformations, then it can be shown that PQ, this mathematical quantity PQ, can be written as 1 minus 3 q square rg, radius of gyration, whole square, where q can be written as 4 pi by n lambda sine theta by 2, and you are working at only very small q's, very small thetas. And this type of relation, if you get, so basically this can be mathematically worked out, assuming the ideal chain conformation. You basically take all possible conformations, this is what you get. And if experimentally you measure PQ, and for small q you see this 1 minus 1 by 3 q square behavior, then by fitting you can get out rg whole square, which is the radius of gyration whole square. So this is a method to get experimentally obtain rg square, assuming the ideal chain conformations. And basically this holds when qrg, this quantity, is much less than 1. And what can be shown is that this r theta, what is r theta? R theta is this Rayleigh ratio. R theta by kcm is actually equal to PQ, and when that can be written as 1 minus q square by 3 rg square, right? So which is valid only for dilute solution, and for, I mean, this form can be written for ideal chain. Then by fitting experimentally, you measure this, okay, and if it for small q has this behavior with q, then by fitting you can get the value of r squared g. However, for larger q values, Debye was the person who first calculated P of Q for the ideal chain, averaging over different polymer conformations, right? And PQ, so again ideal chain, and PQ, I think this Gunnier regime, you don't need to actually assume an ideal chain to look at the derivation. But for this long Q, you definitely had to assume an ideal chain. And then PQ can be written as this expression, exponential Q square R square G, radius of gyration whole square, and so on and so forth. Now, if you measure PQ and change the angle so that you keep changing Q and plot PQ versus Q R square G, right? I mean, if you can do a fitting and get it out, because you have for small q you can already get an idea of r squared g, and then pq would look something like this as a function of q r squared g. So here it is the so-called Gunnier regime, Gunnier Guineer regime, and here it would pq will change as 1 minus q square by r squared g, and that's how by fitting you can get r squared g. And once you get this, you can fit that entire thing, and if it does fall like this in this behavior, this is valid only for the ideal chain, and if you can fit it, that means that you are getting an ideal chain, can- ideal chain conformation. If it doesn't fit, it has some other power law decay, then you might get the real chain, right? So this is for large q. Large q means small, smaller length scales, right? So small q is large length scales also, and large q is small length scales. So there it might behave like an ideal chain or a real chains. And so from here, by fitting, by figuring out what is the nature of the drop of the form factor, you can figure out whether it's behaving like an ideal chain or a real chain. And in this case, our g square, square root ratio of length scales, lambda being the scattering light, has to be greater than 1 here, right? So this is valid in this scale. So note that we have been talking about conformations of smaller sections of a chain or of a single chain. And when we are talking about conformations of the structure of a single chain or internal structure of the chain, we typically talk about the form factor PQ. Right now, it can be shown, and we will discuss this later in the statistical module, statistical physics focus module, that PQ, the form factor, can be written as 1 by n, 1 plus pair correlation function g of r. So integral of, so basically this is the Fourier transform of the pair correlation function, g of r into e to the power I q dot r d3r, right? It's a Fourier transform, but form factor is a Fourier transform of essentially the intramolecular, within a molecular g of r. Whereas the term structure factor, S of q, is defined as 1 by n, which is the number of monomers in a scattering volume V. You typically refer to structure factor when you are talking of intermolecular scattering, when you're trying to figure out the conformations, the structure, the GFR of one molecule versus other, and that's when you typically use S of q. P of q is intra, S of q is inter molecular. So S of Q is defined as 1 by n, j equal to 1 to n, all possible basically scattering centers. Again, double sum k equal to 1 to n, sum over all possible scattering centers, e to the power minus I q dot rj minus rk time average. And when I write this, of course, it means that you can work only with the real part of this function, which in this that case will be similar as we saw in the previous case, cos q dot rj minus rk. Right now, if lambda, the scattering wave vector, which can be written as 2 pi by q, lambda is such that the volume spanned by that wavelength. So basically, there's a volume corresponding to the wavelength lambda cube is much larger than the scattering volume. Then S of Q, S of Q, right, will be proportional to n. Why? Because q is then extremely small, lambda is very large, then q is very small, and then basically this is a small quantity, and this into rj, because the scattering volume is much larger than these differences. This is basically equal to 0. Then e to the power 0 is equal to 1, and you have a double summation. So that goes as proportional to n. S of q is proportional to the number of scatterers in the scattering volume, and but in the opposite regime, right, when you are going to smaller and smaller length scales, then S of q, see, S of q is defined just in terms of the number of monomers in scattering volume. So if you had independent scatterers like different polymers, then S of q will be proportional to n. However, if you are going to larger q, so that q is larger than 2 pi by rg, the radius of gyration of a polymer chain, if this is larger, that means you are going to smaller length scales, lambda is smaller than rg, then you are essentially exploring, you are essentially, by scattering, you have information to intra chain, within a chain, because you are going to length scale smaller than rg. And then S of q is equal to n, number of monomers, into pq. So for q larger than cn, cn being the number density, by n, number of monomers in a chain, 1/3, right? So instead of plotting p of q, if you plotted S of q, okay, where you change both theta and maybe lambda, then for very small q, you will get the intermolecular regime, okay. Uh, in the middle, you will get the so-called Gournier regime, and when in this Gournier regime, uh, right, so we discussed the Gournier regime. You can also extract the p of q from there, and from, so this is basically where your scattering wavelength is order of rg, that's the so-called Guernier regime. And for larger q, or even for smaller wavelengths, right, smaller length scales, you are looking at intramolecular scattering, where you can figure out whether the chain is behaving like an ideal chain conformation or like a real chain. So it's the so-called fractal regime, and you're getting information about conformations smaller than the size of a single polymer, right? So basically, structure factor is used the term for smaller q, uh, which means large wavelengths. You're looking at intermolecular behavior, whereas uh, form factor is typically used at large Q, where looking at intra chain characteristics or internal chain characteristics or organization, right? And for large Q, S of Q can be written as NPQ. So this is again taken figure 3.19 from Rubinstein, page 123, and this was S of Q, whereas previously I presented data on P of Q. And finally, before summarizing, I'll just have written down the formula for the form factor. And to notice is though that this is 1 by n squared, whereas of S of Q is given as 1 by n. The rest of the expression j equal to 1 to n number of scatterers looks rather similar, but there's a difference in this is n square and this is n, and intensity at any q can be written as number of scatterers into s of q into some factors which shall depend upon the scattering contrast, whether you use light, neutron source, or X-ray, and the incident intensity. So I'll stop here. I'll start in the next one about, so here I've given you some ideas about how one figures out about the conformations. We shall start later, and there'll be another module talking more about S of Q and how is it related statistical physics wise to microscopic arrangement of molecules. Okay, so with that, I come to an end. Uh, Let me see. Hide sharing. Stop sharing and stop recording.